Okay, so again, as I go through here, I'm going to be highlighting a lot of things, so you might want to do the same. I'm going to be pulling up my graphing calculator, so you might want to do the same. And again, please, 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 any and all questions, I'd love to hear them. Okay, so first off, there are two types of exponential functions. There is growth and there is decay. Technically, there are two formulas, but they just have a different variable. A lot of times when you're graphing, you see a times b to the x. And a lot of times when you're doing word problems, you see a times b to the t because t is time. Please make sure you know that those are absolutely equivalent. Doesn't matter what variable is, same thing no matter what. When it comes to how do you know if it's exponential growth or decay, in order for something to be exponential growth, the b has to be greater than 1. And in order for it to be decay, the b has to be between 0 and 1. Even further, here on the left side, that b has a name, and that is called the growth factor. And over here on the right, this is called the decay factor. So you just want to highlight that b is always the factor, which is different than r, which is the rate. So it's kind of good to know the difference. Mr. Eaton only talked about it briefly, but I want to ensure that you make sure you know that each of these graphs has what's called an asymptote. So if you could please add in that asymptote there on the x-axis. We generally draw asymptotes as a dotted line. Let me give you a quick definition of an asymptote that you can write here. So an asymptote is a value the graph approaches more and more closely but never reaches. In terms of exponential, the asymptote is always horizontal. If it's horizontal, it's always going to be y equals a number, and it moves up or down only. So again, let me just give you a second to write that down. So again, if you're looking for a little bit more of a better definition of an asymptote, it's a value that the graph approaches more and more closely. So it keeps going closer and closer and closer, but it never actually reaches it. When you're talking about exponential functions, it's always going to be horizontal. Something that is horizontal is always going to be y equals a number. And then that asymptote is allowed to move up and down only, never any other way. So keeping that information in mind, if I was to ask you for the domain of either of these, it's always all real numbers, and that never, ever, ever changes, no matter what. In both of these, the asymptote is here at 0. And then the y values are above 0. So that's how you know that it's 0 to infinity in both cases as well. Whenever you're trying to find the range, it always has something to do with the asymptote. So the fact that the asymptote is 0 is why you have a 0 in your range. If your asymptote was 11, you would have 11 in your range. Those two things always have to be matchers, so you might want to just make yourself a note that that's the case. Let me give everybody a hot second just to make sure they've got everything written down. Obviously, you want to know what kind of problems do I have to be able to do, which I'm going to show you in a minute. But any questions so far?
What's the difference between ABX and ABT?
Just what variable you're using. The X is usually used when you're graphing. The T is usually used for a word problem because T is usually time, but that's the only difference. All the other rules about them are the same.
Okay, thank you.
Yep.
How do you know if the asymptote is 0 if it doesn't touch it? Like if it's, like how do you know it's 0?
Well, so the two graphs at the top here, these are, of course, our parent functions. So the fact that I'm telling you that there's 0 in the parent functions, in the next two examples, we're going to see how it can possibly move. And I think your question hopefully will be answered once we try 1 and 2 below. So if not, ask it again. Okay. So let's see these problems and see if maybe it makes a little bit more sense. So take a look here at 1 and 2. It's asking you to create a table of values, graph each one, identify the asymptote, domain, and range. So whoever was just asking me that question, they were asking, how do you know where the asymptote is? Well, here's the thing. The asymptote always starts at 0, and then it moves up and down only. So take a look here at number 1. Do you see this big -5? Hopefully it hasn't been so long that you remember that that big -5 means that this whole graph is going to move down 5. That down 5, that means that that is where your asymptote is. So at -5, you're going to have an asymptote instead of being at 0 because of the fact that there's a -5. So the first thing you might want to do on your graph is add in the asymptote, which again, we generally draw as a dotted line. I can also feel confident in writing that the domain is all real numbers. And then I'm going to leave the range alone for a second just to see what happens. If I look at 2 to the x, I know that this should be an exponential growth problem, but I'm going to find some actual values so I know for sure. So I'm going to find a table of values. And a good rule of thumb is you want to choose a couple positive, a couple negative, and 0. And here's the thing, you can find those values on the graphing calculator as long as you know what you're doing. So I'm going to pull up my graphing calculator. I'm going to go to the y equals, and I'm going to type in that equation. So 2 to the x, make sure you pop out of the exponent, and then -5. Then I'm going to pull up the table. The table you do by pressing the second key and then the graph button. So this brings up the table for you. Look at all these different x's that I can choose, and it's going to give me the corresponding y values. So I'm going to go ahead and take a look as I scroll up and down what is happening to these y values, and take a look at what happens as the x's get smaller and smaller and smaller. So hang on, clicked on something weird. Oops, there's my graph, spoiler alert. We're going to get to that in a second. I'm going to go ahead and continue. Hold on. I don't know why I'm in the Y column and not the X column. Sorry. Okay, there we go. So see what happens as I get my x's smaller and smaller and smaller? Look at those y values, -4.875, -4.938, -4.996. Those y values are getting very, very close to what number?
-5.
-5, which, spoiler alert, that's where the asymptote is. So again, whoever asked me the question, how do you know where the asymptote is? It's the y value that the points are getting closer and closer and closer to. So I'm going to take a look specifically at the values I asked for. So -2, -1, 0, 1, and 2. I'm going to go ahead and copy those onto my worksheet here. So in the y values, which again just came from the graphing calculator, this is -4.75. This is -4.5. This is -4, -3, and -1. And then you're going to go ahead and graph those. So 2, -1, 1, -3, 0, -4, and then getting closer and closer and closer to the asymptote. Once you have the picture in front of you, you can see that the y values are greater than -5. So you can say that the range is -5 to infinity. So questions? So I'm okay if you're using your graphing calculators, but I want to make sure you're using them as a tool and not a crutch. Don't just randomly write stuff down and be like, oh, I know what I'm doing. You have to make sure you're writing stuff down in a way that makes sense. So any questions before we try 2? Okay, just like before, take a look on the outside. If you look on the outside, there is no movement up or down. So if there's no movement up or down, that's how you know the asymptote stayed exactly where it was at 0. It always has to start at 0 and then it can move up or down only. Again, you can feel confident in writing that the domain is all real numbers. It will always be. And then again, we're going to do a table of values. And again, I think a good table of value is -2 to 2. If you look at this 1/3, this should be a decay function. So the points that you pick, they should be decaying. If you want to know what those values are specifically, pull up your graphing utility, go to the y equals, clear the old problem, and type in the new problem. So in parentheses, I'm going to put 1/3. Then up in the exponent, I'm going to put x plus 1. And remember that plus 1 up in the exponent moves you to the left, which does not affect the asymptote. If I press the graph key, it looks exactly how I think it looks. It looks like decay. Again, it looks like it's touching the asymptote, but it's not. You have to be smarter than your calculator and know that it's not touching the x-axis. To find a couple of values, again, I'm going to pull up my table. I'm going to take -2 to 2. And then look what happens as the numbers get bigger. They're getting 0.037, 0.0123, 0.0041. They're getting smaller and smaller and smaller until they are essentially 0. Why 0? Because that's where the asymptote is. So if I go back here, the y values that I get are 3 and 1, 1/3, 1/9, and 1/27. And again, I got those right from the table. You could write them as a fraction or decimal. So -2, 3, -1, 1, 0, 1/3, and then essentially just getting smaller and smaller and smaller, but never quite actually reaching the asymptote. Notice again that the graph is above the y-axis or above the x-axis, which is how I know the range is 0 to infinity. So let me put those just side by side. Notice that for each, I found a table, which you can use your graphing utility. Notice that for both, the domain is always all real numbers. Notice that the growth, the graph is rising. Notice for decay, the graph is falling. And notice that the asymptote either has to be at 0, or if the graph moves up or down, the asymptote moves with it. So any questions on the graphing before we talk about some word problems?
Can you go over how you did that on your calculator, like after you wrote the equation, the y 1, 2, 3, because my screen was frozen.
To pull up the table?
Yeah.
You press second graph.
Thank you.
Yep. Anybody else? Okay, so then on to the word problems. So the only difference between the original equations and these word problems are that instead of saying a times b to the x or a times b to the t, you're now rewriting the b as either 1 plus r if it's growth or 1 minus r if it's decay. That's the only difference from the previous problem to this problem. So again, a is the initial amount. R is the growth or decay rate. And remember, the rate is different than the factor. You have to convert it into a decimal. And then T is time. Remember that your time values have to always be the same. So years and years, months and months, or else you have to do a conversion. The easiest question to ask is number 3 on the next page. So let's say that I give you this equation, and the first thing that I want to know is growth or decay. The way you answer that is by looking inside of the exponential. So 1.23 on the left and 0.57 on the right. If the number is bigger than 1, that's how you know that it's a growth situation. If the number is less than 1, that's how you know that it's a decay situation. To figure out how much the rate grew or decayed, if it's a growth, you're going to do 1 plus r equals the value. And if it's a decay, you're going to do 1 minus r equals the value. On the left, subtract 1, and you're going to get 0.23. 0.23 means 23%, and it's growth. On the right, you're going to do 1 minus 0.57 equals r, so I just put them on opposite sides. So r equals 0.43, which is 43% decay. The initial value is always the A value out front. So the initial value in both of these cases is the starting number, which would be 225 on the left and 135 on the right. And then finally, to evaluate it, you're going to plug in whatever number it says. So 225 times 1.23 squared. And then y equals 135 times 0.75 to the fifth. And then you're just going to use your calculator. You can round it to whatever I say. And if I don't say, you can say 2 decimal places. So on the left, you get 340.40. And on the right, you get 812. So again, when it comes to the word problems, you have to take that growth or decay factor, which is B, and you have to either rewrite it as 1 plus r or 1 minus r, depending on if it's growth or decay. Questions? Okay, some word problems. A recent college graduate accepts a job as an Apple genius. There's a starting salary of $37,954, and you're getting a pay increase of 3%. Is this growth or decay? This is growth because you're getting a raise. What is the starting value? Your starting salary is $37,954. What's your R? Well, 3%, you're going to write as 0.03. Find a model. Well, because this is a growth, you're going to say y equals the starting value, which is 37,954, 1 plus 0.03 to the t. And then they want you to solve it for 10 years from now. So you're going to say y equals 37,954, 1.03 to the 10th. Hopefully at that point, that should be the easy part where you plug it in your calculator. And you're going to get a salary 10 years from now of $51,007.00. So maybe that's a lot, maybe it isn't. It's kind of up to you to decide.
Ms. Lupinski, how do you know where to put the comma?
You just look at the calculator.
Okay.
Like, look where the decimal point is, and then every time you count 3 back from that, you put a comma.
Oh, yeah, okay.
How about property values in Randolph are decreasing 5.3% per year? Write an exponential equation and then tell me how much your $650,000 home is worth in 6 years. So first off, a couple things you want to point out here. You're decreasing 5.3%. You have to take 5.3% and you have to move the decimal place 2 to the left to give you 0.053. So y equals 650,000 Because this is decay, you're going to do 1 minus 0.053 to the t. They want to know how much your home will be worth in 6 years. So 650,000. 1 minus 0.053, you can put that in your calculator. It's 0.947 to the 6. And then again, if you plug that in, your home is going to be worth $468,827.66. And guys, something really, really important here. If you tell me that the problem is growing, make sure your salary after 10 years is higher than you started with. If your property values are decreasing, make sure your home is worth less than you started with. A little bit of common sense goes a long way. Questions? Okay, something kind of special we haven't yet seen. Here in the last one for bacteria, they're telling you you have 1,000 bacteria and they are doubling every hour. We haven't seen that word doubling yet, but we might see it again. So here's what I want you to know. Anytime something is doubling, it's 100% growth. Anytime something is tripling, it's 200% growth. And the pattern would continue for quadruple and whatever. So when they tell you that R is doubling, or when they tell you that this is doubling, that means that R is 100%. If you take the decimal point, which is behind the 0, and you move it 2 spots, you're going to get that R is 1. So again, double means 100% growth, but if you convert that to a decimal, you're going to get 1. If you do it for the tripling, you're going to get 2. So all that means is that when you go to write your equation, you're going to get 1,000 bacteria to start. Because it's growth, you're going to do 1 plus R, which in this case is 1 plus 1 to the t. If you add 1 plus 1, you're going to get 2, which should make sense because you're doubling. You now want to solve for 10 hours and 12 and a half hours. So for 10 hours, you're going to do 1,000 times 2 to the 10th. Then you're going to do 1,000 times 2 to the 12.5. And again, at that point, it's just a calculator problem. Bacteria, grow really fast. I mean, just think about the coronavirus. So turns out after 10 hours, there's going to be 1,024,000 bacteria. And so that's the answer for 10 hours. And then after 12.5 hours, there's going to be 5,792,619 bacteria. I'm rounding them to the nearest whole number because you can't have part of a bacteria. But this idea of doubling and tripling is pretty important, so I would just make sure that you have jotted that down. And then let me give you another second just to catch up if needed. Any questions? And if you miss anything, guys, you can go back. This is in class notebook, so if you miss anything, you can go back later, and I'm going to post it as well. Once you've got all that, look at the third page. This is just about compound interest. Remember, you are only going to use the compound interest formula when it specifically says compound interest. Here is the formula, which you have written down already, but here it is again. And then here are just some reminders. A is how much you have at the end. P is how much you initially invest, which is the principal. R is the interest rate as a decimal. N is the number of times you compound per year, and T is the number of years. And a little note here, you can only have T values in years. Mr. Eaton kind of mentioned them in passing, but I typed them all up for you here. These are all the different possibilities for N. So if it's compounded once a year, N is 1, semi-annually is 2, quarterly is 4, monthly, weekly, and daily. So from this point forward, if you need to refer to these N's, feel free to do so. And then just some general things. The more money you invest, the more interest you make. The longer you invest, the more interest you make. And the more frequently you compound, the more money you make. Hopefully, this is all common sense, but I figured it doesn't hurt to write it down. So again, you technically already know everything I just went over in those boxes, but I figured it wouldn't hurt to kind of put it all in one spot for you. And then what is it you're supposed to do with it? Well, you're supposed to answer a question like number 8. You deposit $9,000 in an account that pays 1.4% interest. Find the balance after 3 years if you're compounded quarterly. So if you're compounded quarterly, there are 4 quarters in a year, just like there are 4 quarters in a dollar. So you're going to set up A equals $9,000, 1 plus, you're going to take this 1.4% and you're going to move the decimal point 2 to the left. N in this case is 4 because there are 4 quarters. And you're raising it to the 4 times 3. And hopefully it makes sense that 4 times 3 is equal to 12. I think writing the formula is the easy part. I think putting it in the calculator takes a little bit more work. So I'm just going to review with you the steps in the calculator. So if I pull up the calculator and if I go back to the main screen here, always start by doing the division. So 0.014 divided by 4. Hit enter. Don't do anything else. Then do plus 1. Then raise it to the 12th because 12 is 4 times 3. Multiply it by 9,000. And that's your final answer. $9,385.36. And again, have some, common sense here. You should not be a millionaire after investing for just a couple of years. Questions? You guys still with me?
Yeah.
Okay. Okay, so then to explain a little bit more about where E comes from, again, you don't really have to know this part, but basically, if you take the compound interest formula and you assume that you are compounding more and more frequently from once a year to once a month to once a day to once a minute to once a second, you're basically taking the compound interest formula and you're evaluating for larger and larger and larger values of N. And if you do that a bunch of times, you essentially get closer and closer to E. Again, this explanation part is more of a pre-calc thing. So it's there if you want to look at it. It's there if you want to read it. But at the end of the day, all you have to really know is that it gives us a second compound interest formula that you're only allowed to use if you see the magic words compounded continuously. So if you see the words compounded continuously, you have to use that formula that looks like per. So in number 9, what's the balance if you are compounded continuously? Though again, those are the magic words. So you're going to say A equals $5,000. E, you're going to take that 2% and you're going to make it a 0.02, and you're going to do that for 10 years. And that is easy enough to just plug into your calculator exactly as it is. And that will give you $6,107.01. And again, if you're investing $5,000, you shouldn't have $1 billion at the end of it. So make sure you use a little bit of common sense there. questions before we go ahead and finish up? Okay, simplify the expression. This just means use the properties of exponents. So in number 10, if you have like bases, you're going to add those exponents. You're going to get e to the 8th. In number 11, you're going to divide 11 by 22. You're going to simplify, and then you're going to simplify the e's. So if you do 11 over 22, that becomes 1/2. If you subtract the e's, you're going to get e to the -1. You don't want e to a negative exponent, so you're going to move it to the bottom, which is going to give you 1 over 2e. And again, just to clarify why that is, 11 over 22, the bigger number is on the bottom, which is why you wind up with a number on the bottom. If you look at the e's, there are more e's on the bottom. By how much? By 1. In number 12, give that 4 to both. So 5 to the 4th, and then e to the 28x if you multiply. 5 to the 4th is 625, e to the 28x. That's it, nothing else to do. When it comes to graphing with e's, they follow all the same rules as the other graphs, including the rules for asymptotes. So that means they start at 0 and they can only move up and down. So again, in each of these problems, you might want to add in that asymptote. Very easy way for you to know if it's growth or decay. It's growth if there's a positive exponent, and it's decay if there's a negative exponent. That's it. So again, look at 13 and 14. If you look at 13 and 14, see this -4, see this +2, that tells you where the asymptote is. So in the one on the left, the asymptote is at -4. The one on the right, the asymptote is at 2. Just like on page 1, they have to start at 0 and then they can only move up or down. So the asymptote is -4 and +2. Domain is always all real numbers. To figure out points, you're going to use the graphing calculator. I'm kind of running out of time, so I'm going to skip that part. So if you were to plug number 13 into the graphing calculator, you're actually going to get a graph that looks like this. It's upside down because of the negative. That means that the range is underneath -4, which is -∞ to -4. Over on the right, you're going to get a graph that looks like this, which means that the range is above 2. And again, if you want to confirm these, just use the graphing calculator. I'm going to run out of time.
By graphing calculator, you mean to like find the x and y values like before?
Yep. So like if I go to my graphing calculator and I go to the y equals, I would do bring up the e, or so wait, it's like if I want to do number 13, I would type in negative and then bring up the e and then to the x, and then make sure you pop out of the exponent, -4. You can pull up the table, and all the values are pretty much going to be decimals, which are fine. That always happens when it's e. And then if you bring up the graph, you just go ahead and sketch it.
Thank you.
Yep. And then the last two, so these last two, again, this is what happens when you want to take it from something with an E and rewrite it to something not with an E. So in order to do that, you're going to take your problem, everything that has the E and the X or the T, you're going to move those to their separate. So 44 and the X, and then A and the X. So you're going to rewrite this as leave the A on the inside, leave the X or the T on the outside. In number 16, leave the 44 on the outside and leave the X on the outside. And then put everything else on the inside. So E to the 0.62 and E to the negative 0.45. Again, you always want the A to be out front, whether it's an A or a number. You want the variable to be up by itself, whether it's a T or an X, doesn't matter. You're now going to calculate this in your calculator. So if you do E to the 0.62, you're going to get 1.86. And if you do E to the negative 0.45, you're going to get 0.64. 1.86 is bigger than 1. So 1 plus R equals 1.86. 0.64 is less than 1. So you're going to do 1 minus R equals 0.64. Subtract the 1, you're going to get 0.86. Subtract the 0.64 to the left and add the R to the right, and you're going to get 0.36, which means your final conclusion is that on the left, it's 86% growth. Why growth? Because it's bigger than 1. And on the right, it's 36% decay. Why decay? Because it's less than 1.